9.3 has us working with adding and subtracting square roots together. Now the rules and properties that we have with adding and subtracting square roots together apply to something other than just a square root. These same rules and these same properties apply to if I'm adding and subtracting cube roots, fourth roots, tenth roots, and really any kind of radicals that we might be seeing in our math classes or math homework. So the main rules that we need to follow are listed right here at the very top. If the index and radicand of two radicals are the same, then the coefficients can add and subtract together. I want to make it very, very clear here that it's the coefficients specifically that are adding, subtracting together. A big warning that I will give you with this, and this generally tends to get a lot of people as they're going through this section and these types of problems, is we tend to think that because I'm adding, subtracting things, the index and or the radicand must also change, when it turns out the index and radicand will actually never change when we are adding and subtracting radicals together. This applies to square roots, cube roots, fifth roots, 40th roots, any kind of radical that's being added or subtracted together. We will never see the index or radicand change in the addition and subtraction process. Now beyond this, we're going to follow all of the previously learned and discussed methods for simplifying something down. We are going to be using PEMDAS in our order of operations to go through and simplify these things. So go back and reference our previous sections in the previous videos that talk about how we use radicals inside our order of operations. Remember that everything inside of the radical, that's the radicand, corresponds with the P portion of PEMDAS, that's our parentheses, and then actually applying the radical itself is the exponent, or the E portion of PEMDAS. So with that in mind, let's go ahead and take a look at our four examples here. So looking at our first example, we have 7 square root 11 minus 10 square root 11 plus square root 11 here. Now again, our big requirement for adding and subtracting square roots together, but again, radicals at large, is that the index of all radicals that are adding and subtracting together are the exact same, and that the radicands, the things inside the radicals themselves, are the exact same. So because both of those conditions are met with our first example, that means we can add and subtract the coefficients together accordingly. Remember that in this process, the index and the radicand will never be changing if I'm adding and subtracting things together. So we have three things adding and subtracting our first example. I'm going to do two at a time, so I'm just going to add these first two things together. And I'm only adding the coefficients. So I have 7 minus 10, that's going to give me negative 3. The square root 11 comes down exactly as it was. In this instance, it's not changing. Remember, index and radicand don't change. And then the square root 11 at the very end, I haven't done anything with it, so I'm just leaving it there for now. And now I can get to it. I have a negative 3 plus this invisible 1 that's written in here. So negative 3 plus 1, that's going to give me negative 2. Index and radicand don't change. So I get a final answer here of negative 2 times the square root of 11. In our second example, we have just two things that are adding and subtracting together here. So I'm always looking at the index and the radicand first to see whether or not I can add or subtract anything together. And it turns out that the indexes of both of these things are the same, and the radicands are kind of similar. They both have this b to the 5th power, but one is a 48 b to the 5th power, the other is a 75 b to the 5th power, meaning that these two radicands are different, and therefore, at this point in time, I cannot add or subtract these things together. So, my only option then is to simplify these radicals down as much as I possibly can. So starting off with the first one, let's go find the prime factorization of 48. I think that tends to help as we're going through and trying to cancel these things out. So like we've done in the previous videos, let's go ahead and find the prime factorization using this prime factor table. I'm seeing how many times 2 goes into 48, so 2 goes in 24 times, 12, get to here, and now 2 doesn't go into 3 anymore. The next prime number is 3. 3 goes into 3 once, and here I now have the prime factorization of 48. 2 times 2 times 2 times 2 times 3. I'm noticing that I have a perfect square here, and I have another perfect square showing up here. Those two things are going to cancel out, and then be brought out front of the radical, multiplying together to give me 4. There's a 3 left over in this prime factorization, and because it's not a perfect square, it's just going to be left over inside of this radical here. Let's take a look at the 75 in the second radical. We're going to do the same thing we did with 48. We're going to find the prime factorization of that. So again, making that table. And there's a lot of different methods that you can use to find this prime factorization of a number. This is just one of them that I really like to use. You're welcome to use a different one if you would like. Okay, so we didn't need that much, the line there. Let's erase a little bit of that. There we go. So now, from here, we have our prime factorization of 75. We're noticing 5 times 5 is a perfect square. So if that is a perfect square, then I can bring that out front for that second radical. And then I have this 3 left over. And that's just going to go left over inside here. And now, at this stage, I'm noticing that the indexes are still the same, and now the radicands are the same also. So because the index and radicands of both radicals are the same, I can therefore combine the coefficients together. You also have the choice, and looking at this you might be noticing this, I can further reduce this b to the 5th power down. And at this point in time you need to make the decision for yourself of, are you going to simplify the radicands all the way down individually, or are you going to combine them together to be one single radical and then simplify that down? Really, it's your choice. I'm hard-pressed to say that one is always better than the other. It's going to depend on the problem and the information you've been given. So for the purposes of just showing one of those options, for this problem, let's combine everything together to be one single radical first. So I combine 4 and -5 together to give me -1 down here. And now I need to further simplify this radicand down a bit more. The 3 is already a prime number. I can't do anything with that. But this b to the 5th, I could rewrite for myself. Oops, b to the 5th. So b to the 5th is the same as saying b squared times b squared times b. We notice we have a perfect square here and a perfect square here. So the square root of each of those is a single b, and those come out front multiplying together, which creates a b squared out front. We have this one extra b left over here. That has to go back inside the radicand. I can't do anything with it. I can't cancel anything with it, so I can't just drop it entirely. I have to leave it in the radicand spot. But from there, we can't do anything else. We got our final answer of -b squared times the square root of 3b. So here in example 3, we're going to go through and simplify these 3 radicals down by adding and subtracting them together in a slightly different way than we did in example 2. In example 2, we combined those 2 radicals together partway through the problem and then simplify at the very end. What we're going to do here in this problem is instead simplify every single radicand down as much as we possibly can and then add and subtract these things together. Either route that you would like to take in your problems as you're going through them works. It's a matter of just picking one and committing to it for that specific problem. So let's take a look at this. Start with simplifying each individual radical down. So the square root of 36x to the 7th. Well, I know 36 is a perfect square, so that would come out front as a positive 6. This would become 2/3 times 6 times the square root of x to the 7th. I'll deal with that x to the 7th here in a moment. Second one, 16 is a perfect square. The square root of that is 4, so that's going to come out front. I'm going to have the square root of x to the 7th left over. And then the last one, I also have that x to the 7th that's in there. And now, again, I'm noticing that my radicans are all the same, and we could add or subtract things together here, but instead we're going to simplify all of these radicals down even further, and then make adding and subtracting the final step that we do. We're going to really, truly, and entirely follow PEMDAS and the order of operations as we're going through these problems. Now, looking at x to the 7th, put this off to the side here, I could rewrite this as x squared times x squared times x squared times x. And we notice we have 1, 2, 3 perfect squares here. So each of those would come out front as an x. Because I have 3 x's multiplying together, that would become x to the 3rd. So each of these new coefficients are going to be, with this first one, 2/3 of that, it's going to be 4 x to the 3rd square root of x. Again, I still have this x left over here, so I have to leave that inside of each radical. I'm getting, it's going to be 16 over 3, yeah. And then x to the 3rd times the square root of x. And then minus 1/3, x cubed times the square root of x. There it goes. Let's clean up this 3 down here a little bit also. Okay, so now we can start looking at what we can add and subtract together. And generally speaking, we would want to go left to right with that. But really, as long as we are adding and subtracting things with keeping the signs in line, we can do that also. So I'm going to combine these two together here because I'm going to have 16 minus 1 showing up. That's going to make that 15 over 3. And that 15 over 3 is going to simplify down to just being 5. Between these two things, the 16 over 3 being a positive is the larger, so I should still have a positive answer left over there. And now, from here, I'm looking at this and seeing, well, index is the same, radicand is the same, so I can once again just add the coefficients together. I have 4x cubed plus 5x cubed is going to give me 9x cubed. And just like the other ones, the other parts of the process, the index and the radicand do not change when I am adding or subtracting things together, only the coefficients. And when we do that, we get a final answer of 9x cubed times the square root of x. And looking at our final example that we have here, we now have the square root of 48 plus 2 times the square root of 3. Once again, I'm looking to see is the index and the radicand the exact same with these radicals. We're seeing the index is the same, the radicand isn't. So I cannot add or subtract these two things together. My only option is to simplify this square root of 48 down and see what I could get, and maybe I could add or subtract something together later on in the problem. So let's find the prime factorization of 48 like we've done in the past. It's in our table. So 2 goes into 48 24 times, 2 goes into 24 12 times, 2 into 12 6 times, 2 into 6 3 times. Pick the next prime number, that's going to be 3. 3 goes into 3 once, so I have my prime factorization listed all right here. I'm seeing that I have 2 perfect squares showing up here. Then I have a leftover 3 inside as well. So these 2 perfect squares, square root of 2 and square root of 2, those are going to come out front, multiplying together, which is going to give me 4 times the square root of 3 plus 2 times the square root of 3. Nothing changed with the second radical. It's already as simplified as it can be, so I'll just leave it there as it is. And now I have the same index, For these radicals, they both have an index of 2, or a degree of 2. Both have a radicand of 3, which means the coefficients can add together. That's going to be a final answer of 3 times the square, it's going to give me a final answer of 6 times the square root of 3. And that's all we can do from there. So wrapping things up for section 9.3, remember that our big requirements are to make sure that we have the same index and radicand between two radicals if we are going to add or subtract anything together. Now again, our examples worked with the square roots, but these same rules and the same processes and all of that apply to if I have the cube root of something, the 5th root of something, the 10th root of something, anything like that. Just make sure you're taking it slow and steady, doing it piece by piece, part by part at a time. We have some extra problems down here. If you'd like to practice any of those, I'd recommend pausing the video here if you'd like to give these a shot. Otherwise, we're going to scroll on down to see what our final answers are for these problems here. So here we have our final answers. Hopefully you are noticing, if you went through them, that a couple of these ones that we have here, we cannot actually add or subtract them together. They have to stay separated. And again, that comes down to the fact that the radicands are different from one another. That does happen on a fairly regular basis. It's not uncommon. It's not that you've missed something, or you aren't doing something, or there's a trick, a gotcha thing that's going on with it. It just happens to be that that's the case with that problem, and that's all that we can do. So that's everything we have for the 9.3 material.